Hello everyone, our project is on self-supervised image classification. The problem we are trying to solve is how to train a good deep learning model with a lot of images, but only a few of them having human annotated labels. Traditionally, image classification requires a large amount of label data, but labels can be expensive to generate, for example, in biomedical imaging or when dealing with panorama images. Solving this problem can have a great impact in those fields. This is when self-supervised learning comes to the rescue. In self-supervised learning, we first train the model on a pretext task with unlabeled data, and then fine-tune the model with a small amount of labeled data for a specific downstream task we are interested in. Our work is based on the current state-of-the-art model, Dino.
One important related work is the knowledge distillation. The main idea is to distill the knowledge from large teacher to small students and train the students to mimic the teacher. We will forward path through the teacher network with momentum encoder and back propagate through the students only.
Another important related work is how the teacher network is updated during training. Teacher network is updated through momentum encoder, which is an exponential moving average of the parameters of the student network.
The current state-of-art model is called Dino. This framework adopts the labelless knowledge distillation idea originated from Bootstrap Your Own Latents. The teacher network will be updated using a moving average of the student network. Using Dino as a baseline, we proposed this framework as shown in the diagram. A sample image will generate different views using data augmentation. Each view will be fed into the student or the teacher network. The loss function was defined to minimize the distance between student and teacher networks predictions for different views of the same image. We are benchmarking two different architectures for student and teacher, Visual Transformer and DenseNet, and this decision was due to their superior feature extraction performance. VIT is a transformer-like architecture for image data, and it utilizes self-attention. DenseNet is similar to the ResNet, but each layer is connected to every preceding layer, which further alleviates the vanishing gradient issue. On top of that, we're adding random erasing into the data augmentation step. Instead of cropping an image into local views, the random erasing will generate random rectangles on the image, preserving the overall image structure. We hypothesize that this technique will complement random cropping and help improve the model performance.
In addition, Dino takes 2 8-GPU servers and 3 days to train, which is too much computational resource for us. So different from them, we used a small version of the ImageNet, which contains 100,000 64 by 64 images. This still requires a long time to train, but it's more manageable.
This is the result of the training loss, and this is the accuracy curve. We made comparison among different k-values on separate models, where RE means the random erasing with VIT, OA is other architecture, which is DenseNet, and K equals to 200 will help us to achieve the better performance. This is the comparison of different models, VIT, DenseNet, and VIT with RE. VIT with random erasing has the tendency to improve the performance. And this is the table summarizing all the results. Random erasing obviously improved the performance.
Our other results are based on comparing attention. Surprisingly, we found that even trained with 64 times 64 images, the model using visual transformation can produce reasonable attention plots on larger images. We use 6 attention heads for the plots. With and without random erasing, the attention plots of the dog are slightly different, but we can see the attentions on the edge of the object. We are also able to generate attention on an image we took. Look familiar? This is CMU's Walking to the Sky. Feel free to try it out on your own picture. In a nutshell, we come to the following conclusion. After imposing experiments on 10 to 200 KNNs, we found out that visual transformers and DenseNet lead to similar accuracy. In addition to traditional BYOL image augmentation techniques, adding random erasing and data augmentation has the tendency to increase model performance. Last but not least, training on small images can produce attention on larger images. This could have further advantages on reducing training time and also data storage. Thank you for your listening.